This question is given in GATE 2012. The question is very big, but the answer will be very small. Anyway, I'll read it out and explain it for you, and even I'll solve the solution. If you feel that the question is too big, please don't copy it down in your book. It's waste of time. You can write it as GATE 2012 question based on TSL. You can find this question in any book. I'll just read it out and explain for you and then solve it. Now watch this one. They are saying that fetch and add is a function which is taking two arguments, x comma I, is an atomic read, modify, write instruction. Read, modify, write instruction means we are going to read it and then modify it and then write it back. Everything will happen in a single instruction without any preemption. That is the beauty of TSL, right? I told you TSL is it will load it and then write the value as a single operation, right? So read, modify, write is going to happen as the same instruction. It is a kind of TSL, not exactly TSL, right? Now they are saying that it is available instruction that reads the value of the memory location x, which means whatever is there in the x, it is going to read it and then increment it by a value of I. So whatever is I, it is going to increment it and return the old value of x. So how does it work is, if you call it as, let us say, if x is initially 10, and if you call it as fetch and add 10x comma, let us say 2, then what happens is the original value 10 will be returned to you and 10 plus 2, 12 will be set to the x. That is how it works. Are you understanding it? So whenever you call fetch and add, the original value which is present in x, that will be returned to you, right? That is what they are saying. Reads the value of memory location and then increments it by a value of x and returns the old value of x. So you are going to get the old value of x, which is 10, but then the value that will be present in x now will be 10 plus 2, which is 12, right? And next one is, it is used as shown below. So they are showing that entire code here, and then they are saying L is a unsigned integer. So they are using actually to fetch and add, they are sending a value of L, argument L, where L is a integer and it is initialized to 0. The value of 0 corresponds to the lock being unused. So here whenever L equal to 0, it means lock is available, and whenever L equal to 1, it means lock is unavailable. It is same as lock variable, right? And now they are saying that this is the code, acquire lock, release lock, which means it is the entry section and it is the exit section, right? So before the CS, the critical section, we are going to put the acquire lock, and after the critical section we are going to put the release lock. Now if this is used, they are asking some questions about it. What about the synchronization mechanism that we get from this? Now I think you understood this question, right? So the question is simple. Okay, I'll just erase it and I'll tell you what this means. I'll just use it here. You please refer to the question. It is GATE 2012 question. They are saying that we have an operation which is fetch and add x comma I. This operation works like this. Assume that initially x value is 10. Now if I call fetch and add x comma 2, then what happens is this will return a value of 10, the old value of 10, as well as it will set x equal to x plus 2, which means x equal to 12. This everything will happen in an atomic unit, which means when you are reading, updating and storing, no preemption will take place. That is the meaning of it. Now using this, they are trying to implement a synchronization mechanism, right? And for that they are using a lock L, which is initially 0, right? And anyone who wants to go into the critical section should acquire the lock. So before entering the critical section, someone will call the acquire lock. Now how is that working? While fetch and add L comma 1. So what does it mean? So we are going to read the value of L. So whenever the first one calls this, then it is simply they are going to get 0 because they are going to fetch it, and then they are going to add 1, which means they are going to make L equal to 1 and they are going to come out. Watch it. See this line. Whoever calls this line first will definitely get a value of 0 if L equal to 0, and automatically L value will be made 1, right? Therefore this while loop will break. When the while loop will break, you are going to come out of the while loop, right? The reason is here it is 0 and you are going to come out of this. Anyway L is made 1, isn't it? And therefore they can enter the critical section. So critical section will be here, right? So whoever calls this fetch and lock first, or whoever enters this while loop first, will get into the critical section. Now the value of critical section the value of L is 1, isn't it? The value of L is 1. Now next time if anyone calls this fetch and lock fetch and add instruction, what happens is they will get a value of 1 here, and then the lock value will be changed to 1 plus 1. Previously the value of lock is 1, and now the lock value will be, L value will be changed to 1 plus 1, which means the new L value will be 2. What you get is 1, but the new L value will be 2, and you will be in the while loop, and while loop will make L equal to 1 again. So what happens is, as long as someone is inside the critical section, or someone has made the lock value as 1, the next process which comes and executes that acquire lock will continuously do this. They will read the value of 1 and change the L to 2, right, because we are going to add plus 1, and then we are going to execute again L equal to 1, which means it will again be made 1, and again we will go back to this loop and again read the value as 1 and again change it to 2 and again make it 1 and again read it as 1. So this one will keep on happening, which means L value will be 1 and then 2, again 1 and then 2, again 1 and then 2, right? So this will continuously happen. So as long as someone has made the value of L as 1, any other process which tries to enter this while loop will continuously toggle between these two values, 1 2 1 2 1 2, like this, right? Therefore all the other processes will get blocked in the while loop. They will all fall in the while loop. Then what about the value of L? Any number of processes, any number of times they execute while loop, L value will toggle between 1 and 2, right? And they already told you in the question that any value which is not 0 is equated to the lock not being available, right? Anyway all the processes are going to be struck here, right? And whenever that process which has made L equal to 1 initially, when it leaves the critical section, then it is going to make L equal to 0. So once it makes L equal to 0, some process which is struck here will come out and enter the critical section. Understood this? Okay, so I'll just tell you what happened here again with an example. See this? What I mean to say is, assume that initially L equal to 0, and now P1 is executing. P1 got the chance. Then what P1 will do is, it will read the L equal to 0 and come out of the while loop, but then it will execute fetch and add at least once. Therefore L value will be made to 1, right? And now after making L value equal to 1, it will come out and it will enter into the critical section. As long as it is inside the critical section, let us say P2 came. Now P2 will enter the while loop, and in the while loop what it will try to do is, it will read the value of L, and which will say it is 1, and then it will add a 1 to it, which means it will become 2, and again in the for loop, in the while loop itself, it will make the value of L as 1, and again it will read the L as L, and then again make it add 1 and again make it 1. Read it, add it, make it 1, read it, add it, make it 1, and P2 will keep on falling in this infinite loop. Let us say again P3 came, and it also wants to enter the critical section, and therefore it tried the acquire lock. It will also fall in infinite loop, isn't it? It will read the value of L, which is 1, right? And sometimes it could be either 1 or 2. Sometimes what happens is, whenever a process has made the value of 2, the value of this one as 2, it might get preempted. Therefore if it is 2, it will become 3, anyway it will become 1 again, right? So initially it will be 1, assume that, then it will make it as 2 and test it, right? And again it will make it as 1, and it will also fall in this loop. So any process which enters the while loop, while some process is in critical section which made L equal to 1, all the process will fall in this infinite loop. They all will wait in the infinite loop, right? So if one more process comes, it will also wait in infinite loop the same way, right? Any number of processes, they will all be in the infinite loop, and whenever these processes get scheduled, they will just be busy waiting. Therefore it is a busy waiting solution, busy waiting in the while loop, and whenever you schedule them, they will enter the while loop and stay there, right? And finally at some point P1 leaves the critical section, and then whenever it leaves the critical section, it will release the lock, which means it will make L equal to 0. Then who will get the chance to enter the critical section next? Any one of them, right? It need not be FIFO order. Whoever gets the scheduling next, which means depending on what the scheduling algorithm selects the next process as, that process will enter the critical section. Let us say the next one selected is P4, then P4 will definitely enter the critical section. It will read L equal to 0 and it will make L equal to 1 using that while loop and will enter the critical section. So the one problem with this test and set lock is, whenever these many processes have attempted to enter the critical section, it is not that the first one which is attempting to enter the critical section will get the first chance, which means even though the process required the critical section in the order P1, P2, P3, P4, the order in which they enter the critical section can be anything. And then P2 will get scheduled, it has to wait, and again P4 when it comes out, P3 will enter, and then P2 will again schedule and will fall in infinite loop, right? Therefore this is the disadvantage. It is going to definitely have mutual exclusion, which means whenever one process is inside the critical section, no other process will enter it, but then it will some of the process will definitely starve. So starvation is still there, right? So how can we avoid the starvation is, it would be if you have one more data structure, right? Along with this, if you have one more data structure, let us say a queue, and in that queue if you can make a list of who are waiting like this, right? It is like this. In real world, if you want to take the example of that room, so let us say this is a dressing room, and now one process is inside the room, and the door is locked, and all the other processes, if they are standing in a line in a queue, right, and in such a way that when he comes out, then only next one can go. If this is the case, then there is bounded waiting, there is no starvation, because everyone will get the chance after some time. But it is not like a queue and everyone are standing randomly and they are pushing like in railway station in India, when people try to get into the trains, they'll follow no queue, right? Then what happens? Everyone will be pushing around, and whoever gets a chance to enter, they will enter it. So there is no fair game there, right? Then what happens? Some process might starve forever. Some person might never get a chance to get inside it. That is what is happening here, right? So in order to resolve it, in order to solve this problem of starvation, some mechanisms what they do is, whenever a process is inside the critical section, let us say P1 is inside the critical section, and then when the next process try to attempt to get into the critical section in this order P2, P3, P4, then they are going to mechanisms are going to add the remaining process in the queue, right, inside the queue, in such a way that whenever this P1 comes out, the next one which will be taken will be P2, right, and next one which will be taken will be P3, just like how it happens in the maybe you can say how it happens in the real world trial rooms. In trial room you might see it, right, in this shopper stop and all. If someone is inside the trial room, then all the other people will wait in the queue, and whenever he comes out of the trial room, the next one will go, right? But then the solution is not like that. There is no process are not standing in a queue, no one is maintaining a queue. Then what happens? Anything can be chosen randomly by the operating system, and it can be scheduled next, and that can enter into the critical section. It is like this. It is like Indian Railways. In Indian Railways, anyone can enter the train without following any queue, isn't it? Whenever a train arrives, everyone will be standing around flocking it, and then whoever gets a chance, you will enter it randomly. Therefore some of the process might start. If there is no queue like this, and if everyone is standing randomly like P2, P3, P4, P5 like this, and anyone can be chosen and sent into it, one process might get very unlucky that it will never get a chance. Therefore there is a starvation. Mutual exclusion is definitely provided, and along with that there is starvation. Now let's see the options, and let's see which one is right. First one is, let's look at the options. This implementation fails as L overflows. Oh, it is a problem, right? So till now we didn't consider about the L at all. Can L overflow? What is L? They are saying that L is a unsigned integer, therefore it has only some fixed capacity. So there is a chance that it might overflow. Let's see in this case if there is a chance that it might overflow. So let's analyze this. Very important. Try to understand this one. Now assume that initial value of L equal to 0, right? And then process P1 entered, and it will read L equal to 0 whenever it fetches. It will fetch L equal to 0 and it will add means it will make L equal to 1 and it will enter into the critical section happily, right? And next one is process P2 entered, right? And it will read L equal to 1, and whenever it executes that first line, this one, fetch and add one time, it is going to fetch the value of L as 1, fine, and then it is going to add 1 to this, which means it will make L equal to 2, and after coming out of this test condition, it is going to increment, make L equal to 1, which means it is going to set L equal to 1. Assume that, okay, let us say this is the case, okay, then what happens, then it will again go back and again fetch it, increment it, set it, fetch it, increment it, set it, right? So this is nothing but fetching it, incrementing it, and this will nothing but setting it, right? So at this point, if it preempts, no problem, then P3 will come and again P3 will do the same thing. It will fetch the value of L as 1 and then it increments it to 2 and again it sets it to 1, right? And if it preempts here, then P4 will come and again it will do the same thing, 1, and it will set it to 2 and then it will increment it to, it will again set it to 1. It will keep on happening. But there will be a problem if there is a preemption instead of this point, if there is a preemption at some other point. See this? Now assume that after executing this fetch and add one time by a process without getting into this statement, if it gets preempted, let's see what happens. Watch this one. Now initially L equal to 1 and now it is incremented to 2, and at this point it got preempted, isn't it? Then what happens? Now the next one which gets the chance is P3. Now P3 will read L equal to 2, and then because it is fetching, right, it is fetching the previous value, and again it will add and then it will make L equal to 3, and if it is allowed to run the next line, it will make definitely L equal to 1, but assume that it got preempted here. Then what happens? Then P4 will come into existence, P4 will come for running, and again P4 will read L equal to 3 and it will make L equal to 4, and if it is allowed to run for one more instruction, it will make L equal to 1, then the problem will be solved. But then if it gets preempted here, right, so on P5 will come and P5 will read L equal to 4 and it will make L equal to 5, and it will get, in case if it gets preempted here. Why should this happen? Remember Graham's law, if something might go wrong, it will, right? Therefore, if there is a chance that it might happen, it will definitely happen at some point of time, right? So you have to handle it. Now what happens? So on Pn, if this thing happens, then L value will become n, and n can be so large that our variable L, this n can be so large that our variable L might not be able to hold it, which means you have started L as all zeros, right, and then 0 0 0 1 and then 0 0 0 0 1 1 0, so on. You have reached the maximum limit, all ones, and again if you try to add one more 1, there will be a overflow, which means it will represent 0 0 0 0, and again either if you don't consider that overflow, the value is again going to become 0 and two processes are going to enter into the loop, or it is going to overflow. Anyway, there is overflow is there, overflow is possible. Therefore this solution fails because there is overflow. Got it? The reason is, instead of adding it 1, they should have set it to 1. See, why should they add it to 1 there and then set it outside 1? Instead of that fetch and add, they could have done fetch and set. That would have been better, right? So what we wanted is, if someone is inside, we just want to make it as 1. Why should they increment it by 1, isn't it? So because of this completely failed. So this one fails because there is overflow. Now next one is saying fails as L can take non-zero values when lock is available. It is not possible. When lock is available, it will always be 0, and it works correctly, but starvation is there and it is not working correctly, right, because L is going to overflow. And then without starvation, no, with starvation is there, right? Therefore the answer is it fails because L overflows. And I think you understood this point, and it is given wrong in many of the books or in all the books. Every book this question is given wrong. You please use your judgment, good judgment, and I have given the explanation, right? You please go through the explanation 2-3 times until you understand it, right? Okay.